Okay, so here's a few of my thoughts on this task and how you might want to use it in the classroom. So I quite like it in that it's quite a low floor type of task in that pupils will quickly find the first two obvious solutions, hopefully. So we've got the 4x3 and then the 6x2 solution. And then at this point you tend to get some really good reasoning from the pupils saying, well, the factor pairs of 12 are 4 and 3, 2 and 6, and then 12 and 1, but my geoboard's only 10 by 10, so I can't fit the 12 by 1 on. So, sir, that's the only rectangles I can fit on this grid. Which is great reasoning, but unfortunately it's wrong because there are two other ones to find. So this next bit of the video has got some spoilers on, so if you want to pause it now and have a look for these two other rectangles, then go for it. And the trick is to start looking on the diagonals. And you might want to, depending on the class, you might want to go through this prompt here of just drawing a sort of a square on the diagonal and ask what's the area of this square, and hopefully they'll realise that two of these triangles make one unit, so the area of this square here is 2 square units, and using that can we build 2 more rectangles with an area of 12 square units. So we can make one this way here, so we can go 2 diagonals across by 3 diagonals, and that's got an area of 12 square units. Again, you can count the pairs of triangles on the outside. So we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And then there's one more to find, which is 1 diagonal wide by sort of 6 diagonals. So 1, 2, 3, 4, 5. Can't quite fit it on that one. I'll put it down here instead. 1, 2, 3, 4, 5, 6. There we go. And again, just make sure that they're okay, that each one of these squares here is an area of 2. So we've got 2, 4, 6, 8, 10, 12. And then that's the solution. We've got 4 different rectangles. None of them are congruent and none of them are overlapping. So that's one solution to the task. But I also like it in that we can link it to surds as well. Now, I've not mentioned surds, so you can do this task without surds, but if you want to have like a really nice visual representation of surds, you can look at, say, this one here, and then this diagonal here. Well, each one of the diagonals is going to be root 2 by Pythagoras, 1 squared plus 1 squared. So this diagonal here will be 2 lots of root 2, and then we're multiplying it by 3 lots of root 2. So you can link it to what we might do when we're multiplying surds. Well, we know this has got an answer of 12. We can actually count the 12 square units, and it links to what we actually do in the abstract when we're doing calculations like this. Well, we've got 2 times 3, which is 6, and we've got root 2 times root 2, which is 2. So we've got 6 times 2, which is 12. And there's other nice links that you can do as well to simplifying surds if you want to. If we look at this longer diagonal here, well, by using Pythagoras, it's going to be 2 squared plus 2 squared, or 4 plus 4, which is 8. So this diagonal here is going to be root 8. So that whole diagonal is root 8, but we also know it's the same as 2 root 2. So we're saying that root 8 is the same as 2 root 2. So that's another way into simplifying surds as well. Why is root 8 the same as 2 root 2? When we take when we simplify that to root 4 times root 2. So you can see we've taken this task quite far. We did the whole task without using surds, but then we've linked it to surds. So it could be a really good example of that behaving mathematically with maturation taking place. So when you do surds, maybe in year 10 or year 11 or something, then you might want to link it back to this task and say, oh, we did this task without surds, but now we've got this new knowledge of surds. Can we see how it all fits together? So I really do like this task, and as usual, any comments or thoughts, just post them in the thread below.